Hello, welcome to this tutorial on reactions of alcohols. Before we start to look at the reactions of alcohols, it's important that we know how to name alcohols and how to classify them because there are three different types. Hopefully, organic nomenclature is something that you're already familiar with and you already know how to name alcohols, but I'm going to give you three examples just to show you how alcohols can be classified and named. So here's our first type of alcohol. This alcohol is known as a primary alcohol, because if you go to the carbon atom that has the alcohol group attached to it, there is an alkyl chain in one direction only coming off this carbon. So it has a hydroxy group or an alcohol group, and it has one alkyl chain. The other two atoms coming off here are hydrogen atoms. This makes it primary. Now, to name this alcohol, we look at how many carbon atoms are in its longest carbon chain. So that's this carbon chain here, and it's got 4. So we begin the name with bute, meaning 4. It has an alcohol group, which is here. So we know it's going to end in ol. And we have to make sure that we're clear on where about that alcohol group is in the compound. So it is on carbon number 1, which is this carbon here. So this one would be butan 1-ol. So we'll have a look at another alcohol with 4 carbons in it, but this time a secondary alcohol. So here's another alcohol. This time, if you look at the carbon atom that has got the alcohol group attached to it, so that's this carbon atom here, it has alkyl groups in 2 directions. It's got one going to the left, one going to the bottom, and the other atom is a hydrogen. That makes this one a secondary alcohol. And we'll look at naming this as well. So if we look at the longest carbon chain, it's still got 4 carbon atoms in it, so it's still going to be named bute. It has still got an alcohol group, so it's still going to end in ol, but this time the position of the alcohol group has changed. So before it was on carbon number 1, now it's on either 1, 2, carbon number 3, if you go that way, or 1, 2, carbon number 2 if you're going that way. We always go with the lowest number, so this is carbon number 2, so this is butan 2-ol. And again, this alcohol is classified as secondary because we're looking at this carbon atom that's got the alcohol group on it and looking at how many alkyl chains are coming off that carbon atom. So we'll look at one more type of alcohol. We'll look at another one with 4 carbon atoms in it. So this is the final type of alcohol, and if you look at the carbon atom that is connected to the hydroxy group, it's got alkyl chains in 3 directions, making this alcohol a tertiary alcohol. So we name this one as well. Let's have a look for the longest carbon chain. We've got 3 carbon atoms making the longest carbon chain. So this one's going to be named on based on prop, which means 3. We know that it's got an alcohol group, which is there, so we know that it's going to end in ol. We need to say where that is, but importantly, we've also got a substituent here, a methyl group. So the methyl group will take a prefix, so it's going to be methyl propanol, but we need to say where the methyl group and where the alcohol group is. So carbon 1, carbon 2, carbon 3, or carbon 1, carbon 2, carbon 3, doesn't make any difference. Either way, the alcohol group is on carbon number 2 and the methyl group is on carbon number 2. So to name this, it will be 2-methyl propan 2-ol. So this is how we classify alcohols. Remember, if you're unsure, you're looking at this carbon atom that has got the hydroxy group attached. That's important because sometimes if you've got a big branched alkane, you might still end up with the alcohol group on the end, so it might look at a glance like it might be tertiary, but if you look at the carbon atom that's got the alcohol group attached, sometimes it is primary, so you have to look very, very closely. So have a little look at this slide, make sure that you're absolutely clear on how you classify alcohols and how you name them, and we'll look at how they react. Well, first of all, we need to know how we synthesize alcohols and where they come from, how you can make them in a lab. So there are 2 main ways of synthesizing alcohols or making alcohols. One of them is a hydration reaction involving an alkene and the other one is through the fermentation of glucose. So we'll go through these one by one. I'll show you the mechanism for the hydration of an alkene, and then I'll show you the process via fermentation instead. So here's the general reaction for the hydration of an alkene to make an alcohol. So we start with an alkene. This is ethene. We react it with water. In fact, when this is done industrially, we actually use steam, so it's done at high temperature. But ethene plus steam, we carry out this reaction in the presence of a phosphoric acid catalyst, so H plus for short, but H3PO4 catalyst, and we produce an alcohol. And one thing that's important to note is this reaction is actually reversible. And initially you don't actually get very good yield, probably get about 5% yield from this reaction, but what you can do is you can take any unreacted ethene and pump that back into the process, and you can actually get quite a high yield from this by recycling unreacted starting material. So you need to know the mechanism, you need to be able to draw this out in an exam, and it does look slightly similar to one of the other mechanisms that you've seen in the alkene topic, so take care with this one, I'll show you how to do it. So we start with an alkene, so we'll just do the simplest one. We'll start with ethene. And in the first step, ethene reacts with the acid catalyst, so we need H plus here. So if you look at an alkene, you've got high electron density around here because you've got a double covalent bond, so you've got a lot of electrons around there, so you've got some area of negative charge, and that's going to be where your mechanism begins, as it attracts towards the positive hydrogen ion. So in the first step of the mechanism, electrons from the double bond attract to the hydrogen plus. This breaks the double bond and opens it up and allows the hydrogen atom to join on to the carbon atom. Okay, so here we've got the beginning of our intermediate. So we've got the 2 carbons and the 4 hydrogens as we began with, but our double bond has now become a single bond. The new bond that was formed is here, so we've got this carbon bonding to the hydrogen from the acid, and this carbon is no longer making 4 bonds. It's lost some electrons, so overall it's become positive, so we need to show positive charge on there, and that's a carbocation. So now we can introduce the water molecule, or the steam, which is going to react with the carbocation. So importantly, on a water molecule, we've got some lone pairs of electrons sitting on oxygen, and these electrons can attract towards the positive charge on the carbocation, which is exactly what happens. So we draw a curly arrow from a lone pair of electrons on water onto the carbocation, the positively charged carbon of the intermediate. So this step forms a bond between this carbon atom here and an oxygen with 2 hydrogens, which is this. So the water molecule adds in here. So this is the next step. But this oxygen here used to have 2 lone pairs of electrons sitting on it in the previous step. And one of these lone pairs has gone to make this covalent bond between oxygen and carbon, which means this oxygen is now electron deficient and it has a positive charge. So we must show that in the mechanism. So this oxygen atom is now positively charged, and that's our next intermediate. So in this step of the reaction, we need to remove one of the hydrogens that was on the water molecule to be able to neutralise that positive charge on oxygen and make sure that all of the atoms have the correct number of bonds. So we take a bond between oxygen and hydrogen and break it, so our curly arrow starts here. These electrons move onto the oxygen atom. This breaks the oxygen-hydrogen bond and releases the hydrogen as an H plus ion. And now oxygen will have 1 bond there and 1 bond there, so it'll be making an alcohol. So here's your product. So we've now got an alcohol. This is ethanol, but remember in the previous step, this hydrogen here was released as an H plus ion because it's lost its electrons because they've moved that way towards oxygen, so we can draw that in the final step. So H plus here has been kicked out from here. So just to make that a little bit clearer, let's highlight this. So this H is coming off and it is now here. And if you look at the start of the reaction to the end, we started with an H plus ion, the reaction's taken place, and we have regenerated the H plus ion at the end, which makes the hydrogen ion and the acid that it came from a catalyst for the reaction. So that's the full mechanism that you need to be aware of. And you may be asked, what role the H plus or the H3PO4 phosphoric acid plays in the reaction, and you just need to be aware that it is a catalyst because it is used at the start but it is regenerated at the end and is not overall used up in the reaction. So there is a second way of synthesising alcohols, and industrially we can use the fermentation of glucose. So you need to know the reaction equation for this. So here's the equation. We have got glucose, aqueous, turning into 2 lots of ethanol, aqueous, and releasing carbon dioxide gas. Oops, I've missed a little bit of balancing out there. There should be 2 lots of carbon dioxide gas. There we go, so that we've got 6 carbons on the right hand side. Now this reaction happens in very specific conditions, and conditions are usually written above an arrow, sometimes above and below an arrow if we've got too much to write to fit it above the arrow. So you need to know the conditions. Now hopefully you're aware from biology anyway that fermentation of glucose requires yeast. And the yeast produces enzymes which carry out the reaction. Because this is based on enzymes, you need to make sure that you're using an optimum temperature for the reaction. So a good temperature for this reaction would be 30 to 40 degrees Celsius. Anything above this and the enzymes will denature and won't work anymore, and anything below this, the temperature is too cold and the reaction is too slow. So if you're asked in your exam for the equation to represent the fermentation of glucose to make an alcohol, please make sure that you write a symbol equation that is balanced, properly balanced, don't forget the 2 like I did, and you need to make sure that you write the conditions above the arrow as well. So with the fermentation of glucose, we get up to about 15% ethanol, and anywhere beyond that, the yeast dies and the reaction stops. So what we do industrially to make sure that we can get some ethanol from this is we get up to 15% ethanol, and then we use fractional distillation to separate the ethanol out and to purify it, and then we continue with the fermentation. So when we got to 15% again, we can distill that off and we can produce more concentrated ethanol. Now obviously in a reaction such as fermentation of glucose, which is very low tech, people do this kind of in their kitchens at home to make either the alcohol for brewing drinks or to make the carbon dioxide for making bread rise. It's very, very low tech, but obviously if once you get past 15% ethanol, you've then got to introduce fractional distillation. It does become more expensive as a method for industrial production of alcohols. So one thing that you might be asked in your exam is to compare or evaluate the 2 different ways of synthesising alcohols. So it's worth having a little checklist of which one's better in terms of the speed of the reaction or the purity of the product and so on. So just a quick run through. The synthesis of alcohols using fermentation of glucose, which is this one, is actually a really, really slow process compared with the previous one, which was hydration of ethene. So in terms of speed, this one loses and hydration of ethene would be better. Again, if you're looking at purity of product, as I said, we can only get up to about 15% ethanol. So you do get very, very impure product, which then needs further processing through fermentation, through fractional distillation. So in terms of the purity of the product, again, hydration of ethene would be the better option. However, when you start to look at the raw materials needed to produce the alcohol using the 2 different methods, the hydration of ethene requires crude oil. That's where the ethene comes from. So crude oil, obviously we know, is going to run out. It is a finite resource, so if you're taking that and then hydrating it to make an alcohol, it's not the most sustainable of options. However, this version with the fermentation of glucose, you're using glucose, so sugars. These are renewable, you can grow them in sugarcane and things like that. So this is a much more sustainable option for producing alcohols. So in that respect, this one is better. And finally, if you look at costs, we tend to do fermentation of glucose in batches, get up to 15%, and then start to process it. So we don't use very expensive equipment. Most of the cost comes into the labour of having to sort out the batch process. So it's cheap equipment, which is a little bit better. If you're to use the previous method of hydration of ethene, that's more of a continuous process. So the equipment to keep that running is very, very expensive. but equally we don't need as many people working on it because it's run by machinery. So in terms of the cost of equipment and cost of labour, they kind of even themselves out a little bit. So make sure that you're aware of the pros and cons of the two different types of synthesis of alcohol. So I've just put those pros and cons into a table, so you can pause the video and have a little look at these if you need to remember them, but you may need to discuss these in some sort of evaluation or compare question. So hydration of ethene wins in terms of speed, it's a faster process, also gives you a purer product. However, the ethene is obtained from crude oil, which is non-renewable, not very sustainable process, so fermentation would be better because it uses renewable resources. In terms of cost of equipment, fermentation is better, but in terms of cost of labour, hydration of ethene is better. So make sure that you're aware of all of those factors. So also in the specification after fermentation of glucose, it's a little bit on biofuels. So biofuels are fuels that are formed from biological material, and there are some advantages and disadvantages associated with using biofuels. So here's a table outlining the advantages and the disadvantages of using biofuels. So if we go for the advantages first, the raw materials are obtained from renewable sources. So using biofuels that come from fermentation of glucose, ethanol that comes from fermentation of glucose is known as bioethanol. That is obviously better than using hydration of ethene because the sugar is a renewable resource, whereas the ethene comes from crude oil, as we mentioned before. So that's one advantage of using biofuels. If you consider biofuels being an alternative to the other fractions of crude oil like petrol and diesel, you can see why a renewable source of raw materials would be better. The other main advantage is that biofuels are considered to be carbon neutral. Because biofuels are made from biological material, which over their lifetime have absorbed carbon dioxide from the atmosphere through photosynthesis, when they're later burnt and they release carbon dioxide into the atmosphere, they release the same amount of carbon dioxide into the atmosphere as they absorbed during their lifetime. So overall, net emissions of carbon dioxide to the atmosphere are not increased by burning biofuels. Now, this advantage comes with a little bit of an issue in that when you're producing biofuels, some of the processes that are used to produce the biofuel do require fuel to be burnt to get those processes going. So although burning the biofuel itself releases no additional carbon dioxide into the atmosphere, the processes used to produce the biofuels do mean that additional carbon dioxide is added to the atmosphere. Now, in terms of disadvantages, one of the main ones is the food versus fuel debate. So if you are growing crops to be able to later burn as a biofuel, then the space you're using to grow those crops could be used to grow crops for food, to feed lots and lots of people. So it's making that choice of whether to use that land to grow biomass to turn into biofuels or to grow food for people to eat. Linked to that is deforestation. So again, the area that you're choosing to grow the plants to be able to turn into a biofuel is often created by cutting down trees. And we know that deforestation, cutting down trees, causes all sorts of problems, including the destruction of habitats. And the fact that the trees are removed means that the carbon dioxide they would be taking out of the atmosphere is not being taken out of the atmosphere anymore. So deforestation is a really, really big problem for carbon dioxide emissions to the atmosphere. Another disadvantage is that of fertiliser pollution. So if you are going to grow crops to produce biofuels, then it probably doesn't seem a bad idea to use a fertiliser. However, you have to be aware that fertilisers that are added to soils to make sure that we can grow plenty of crops for biofuel, they can pollute waterways and things like that. So we need to be very, very careful. They can also produce greenhouse gases, which add to the global warming problem. And the final disadvantage for the use of biofuels is the fact that our vehicles are manufactured to take petrol or diesel. They're not manufactured with engines for biofuel use. So we would have to spend a lot of money and probably burn even more fossil fuels creating factories that can build engines that can take biofuels. So that's a really big issue as well. So you may be asked in your exam to evaluate the use of biofuels in terms of advantages and disadvantages, justifying your opinion at the end. So these are the sort of things that you may wish to talk about in a question like that. Okay, so the reaction of alcohols. We've got dehydration of alcohols as one of the reactions that you need to know, and you need to know a mechanism for this. So dehydration of an alcohol, as it says in the title, dehydration means removal of water from an alcohol. This is the reverse of what we were looking at before when we were hydrating ethene to make an alcohol. This time you take the alcohol, you dehydrate it, and you form an alkene instead. So this is the complete reverse of the reaction that we saw before, and again it uses an acid catalyst. So we're taking ethanol, we are using an acid catalyst to dehydrate it in an elimination reaction, and we're producing an alkene and water. This might seem a little bit odd because before we were looking at how we can turn alkenes into alcohols, so why would you want to go backwards? Well, alkenes are really, really useful for making polymers, and we know from the previous few slides that ethene is generally obtained from crude oil, which is a finite resource and it is running out. So we need a more sustainable option. So if we were to take glucose from a renewable source and turn that into ethanol, we could then take that ethanol and turn that into a renewable source of alkenes. So this reaction is really good. If you use glucose to actually obtain the starting material, it's a good sustainable way of making alkenes, which can then go on to form polymers and other useful products. Okay, so let's take a look at the mechanism of this reaction. We're going to start with ethanol again. Obviously, any of these reaction mechanisms where I'm starting with ethene or ethanol, you could be asked to produce the same mechanism for a different alcohol or a different alkene. So you just need to be prepared to draw out the same mechanism using the same functional group, but maybe vary the length of the carbon chains. So in the first step of this reaction mechanism, again, we start with the acid. And again, we look for any area of negative charge that might react or attract towards this positive hydrogen ion from the acid. So here we've got an oxygen atom with 2 lone pairs of electrons. These lone pairs of electrons can attract towards the hydrogen plus ion. So we draw a curly arrow from the lone pair of electrons onto the hydrogen ion, and that's the first step. So here we've got a new bond formed between the oxygen and the hydrogen, which came from the acid catalyst. And the oxygen atom is now making 3 bonds. It has lost its lone pair of electrons to form a covalent bond. It's electron deficient, so oxygen has a positive charge on it. Now we know from the other mechanism before that if we've got oxygen with a positive charge, we need to neutralise that. If we take one of the hydrogens away, then we just go back to having the alcohol again. So this time, a bond between the carbon and the oxygen breaks. So our curly arrow starts here at this bond, which is going to break. And those electrons move on to that oxygen to neutralise that positive charge. That means that this positive charge can disappear. This bond is broken and we have produced water, because remember this is a dehydration mechanism, dehydration reaction, and it's an elimination mechanism, so we're eliminating this part of the molecule. And this will leave this carbon forming its 3 bonds. So here's your product. So we have a reactive intermediate because this carbon atom is only making 3 bonds, so it's positively charged, it's a carbocation, and we've got the water that has been eliminated from the previous step. Okay, so in the next step we need to make sure that we are neutralising this carbocation. So in order to do that, one of the hydrogens will be removed, and the bond between the carbon and the hydrogen here will break. Those electrons will move onto this bond, forming a double bond. So this curly arrow represents this bond breaking and this bond being made, which means that when there's a new bond here, this carbon will now be making its 4 bonds. This carbon will not be making 5 because this hydrogen has come off and those electrons are going there to form that bond. So this is what it looks like. So here's our final product. I've drawn it with exactly the same bond angles as we had here, just so that you can see which atoms are which. But we can redraw that with the correct bond angles to show that we've got ethene. And we've also regenerated the hydrogen ion from the beginning. So if we highlight this, we had a hydrogen atom here, which has come off as H+, and that's that hydrogen there. So that's regenerated an H+ ion, meaning the hydrogen, or the acid that it came from, is a catalyst. Okay, so there's the full mechanism. We need to remember that it's called an elimination mechanism. And this is because H2O has been removed from our starting material and has not been replaced with anything else, so we've closed it down into a double bond. And we need to make sure that we're aware that the hydrogen is a catalyst again. Now, in longer alcohols, if you were to begin this with something bigger than ethanol, if you started with butanol or something like that, you can end up with a mixture of products. So up here we've got, butan-2-ol, almost. Let's finish it off. I missed the hydrogen out. So if we look at how that mechanism would work for something like this in an unsymmetrical longer alcohol, there are different places where the reactions can take place. So we know from looking at this reaction that when the hydrogen ion is added in, the alcohol group comes off and leaves a carbocation in its place, which is here. So if we look at butan-2-ol, when this comes off as H2O, this carbon will become a carbocation, as shown here. Now, to be able to neutralise that carbocation, we could do a couple of things. So in our main mechanism, you can see that the hydrogen is lost and the electrons in the covalent bond move into here to form a double carbon-carbon double bond. So for butan-2-ol, one option is that this bond breaks, the hydrogen comes off, and the electrons move there, which would give you a double bond right in the middle of the molecule, so that would give you but-2-ene. Alternatively, a hydrogen on the other side could come off and put the electrons into there, forming a double bond towards one end, so this would give you but-1-ene. And then that can be even further complicated by the fact that but-2-ene also exists as EZ isomers as well, so you'd actually get three products. You get but-1-ene, E-but-2-ene, and Z-but-2-ene. So if you're unsure about that, I'd recommend drawing out the full mechanism for the dehydration of butan-2-ol or other long chain unsymmetrical alcohols, just to see how many products you can make, looking at going either side of the carbocation to remove a hydrogen. So that's the dehydration of alcohols. This is something that comes up as a required practical in the A-level course. So you might take an alcohol and dehydrate it in the presence of a sulfuric acid catalyst and produce ethene, because then you would have to distill the product and purify it, which is all part of your list of required practicals. So the final type of reaction for alcohols is oxidation, using an oxidizing agent such as acidified potassium dichromate, and there is a separate tutorial for you to watch on the oxidation of alcohols. So if you want to know about that reaction and the tests for the products, then you can check out this video instead.